Hello everyone, this is Worksheet 5.2, Entropy Calculations of Phase Changes and Chemical Reactions. And I'd like to start by telling you what the entropy of fusion is itself. And we're going to begin by just pointing out, again, the second law. This is equal to an integral over the increments of reversible heat added to the system divided by the temperature. But remember that phase changes occur over constant temperature, so we can pull that T out and integrate over that dq, and this just becomes the total amount of heat that's released divided by T. All right, now if we assume that we perform that phase transition very slowly so that it occurs reversibly and there's no abrupt changes to the state itself, then this is going to be equal to the heat released by a phase transition, which is just the enthalpy change of fusion divided by the temperature. So that's pretty interesting. The same is true of vaporization. This is just going to be equal to the delta H of vaporization divided by T. All right, now the next section concerns what do you do if you know the entropy of a phase change at a certain temperature, but you need to find it for a different temperature. So say that what we want is the entropy of vaporization at 103 degrees C, and this is H2O. So this is superheated water. And the reaction that's occurring here is that liquid water at 103 degrees C forms gaseous water at 103 degrees C, and we want the entropy of that process. But we don't know what the entropy is for that. Say we only know what the entropy of vaporization is at 100 degrees C. And what that equals is going to be 0.118 joules per mole Kelvin. And the way that I calculated this was just to plug in the enthalpy of vaporization and then divide it by the temperature. And the reaction for this one is liquid water at 100 degrees C forms gaseous water at 100 degrees C. And the way that we're going to calculate the entropy we want from the entropy we have is we're going to use a thermodynamic cycle. And remember, thermodynamic cycles are based off the premise that it doesn't matter which process you get from a starting point to an end point. For state functions, what only matters is the endpoints themselves. So we've got the entropy of H2O liquid at 103 degrees C, and the process that we want to calculate for is a phase change, so the entropy of H2O in the gaseous state at 103 degrees C. But we can't do that directly, so first what we've got to do is calculate the entropy of the liquid, bringing it down to 100 degrees C. So H2O liquid at 100 degrees C. So this is the entropy of cooling the liquid, H2O. Then we can calculate what's the entropy of going from the liquid state to the gaseous state at 100 degrees C. And that's that quantity that we know. And then we just need to calculate what's going to be the entropy of bringing the gas back up to 103 degrees Celsius. So the entropy of heating the gas, H2O. And let's say that for this problem I just have 1 mole to make it easy, and also so that we're calculating a molar quantity. And then I look up the molar heat capacities of liquid water, and that's 75.3 joules per Kelvin per mole. And the heat capacity of the gaseous water is 33.6 joules per Kelvin per mole. All right, we've got 3 stages here that we're going to add all together to get the entropy that we want. First, we've got the entropy of cooling the liquid, and we've got the entropy of heating the gas, And then we've got the entropy of vaporization at 100 degrees C. For this first quantity, this is just going to be equal to an integration from the temperature 376 Kelvin up to 373 Kelvin, which is 103 degrees Celsius converted to Kelvin and 100 degrees Celsius converted into Kelvin right up there. And I'm using approximate numbers. I'm not adding that 0.15 just for simplicity. And inside this integral is Cp over T dt. And then if you perform that integration, then what you get is you get Cp log T evaluated at the boundaries, 373 Kelvin, 376 Kelvin. And if you plug this into your calculator, then it all works out to be 75.3 joules per Kelvin, and the mole units canceled out because I'm doing 1 mole, log 373 divided by 376, and this just turns out to equal negative 0.603 joules per Kelvin. All right, so that's that first stage of cooling the liquid. Now, why don't you go ahead and pause this video and take a stab at doing the entropy of heating the gas. It's very similar to the previous step. You're just changing around the temperature, boundaries, and you're also using a different heat capacity. So go ahead and pause now and give it a try. Okay, I'm assuming that you gave it a try. And what happens this time is that we're going from 373 Kelvin up to 376 Kelvin, and we've got a new Cp now divided by T integrated over T. And if you plug in all those numbers, then you get a 33.6 joules per Kelvin times the log of 376 divided by 373. And this should come out to be positive 0.269 joules per Kelvin. All right, and so then what about for this last little stage here? That one is just going to be equal to our delta H of vaporization divided by temperature. And I've already told you that what that's equal to is 0.118 joules per Kelvin. And now we've just got to add these three quantities together to get our final entropy of vaporization at 103 degrees C. And if you add all these together, what it should equal is negative 0.216 joules per Kelvin. Okay, now we're on the other side of the worksheet, and I want to show you how you would calculate the absolute entropy, S, without the delta, at a given temperature. And there is a way to do this, because systems can have absolute entropy. At least they can be calculated even experimentally. So I'm going to show you how to do that now. The equation that you would use is that the entropy for a given temperature is going to be equal to the entropy at the temperature absolute zero. And you might think, isn't that equal to zero itself? Well, it is for a perfect crystal, according to the third law of thermodynamics, but in general, systems do have a non-zero entropy, even at absolute zero. And then you have to add an integration from 0 Kelvin up to our final temperature, and then we've got our heat capacity divided by T, integrated, I'm going to make this T prime to differentiate from our final temperature, and then you just integrate like that. I'll tell you though that in practice it's often not possible to start this integration at absolute zero, so you can approximate it by choosing a slightly higher temperature, like say 10 degrees Kelvin, and that's going to work just fine. All right, so how do you get the standard enthalpy of reaction, entropy, sorry, of reaction? The way that you do that is in the exact same way as with the enthalpy of reaction. And in fact, if you go into the back of your book, you'll see that entropies, S standards, are listed for all of those different substances, and the standard entropy of reaction is going to be equal to the absolute entropy of all the products minus the absolute entropy of all of the reactants. And another way to represent this is that you just sum over all of the products and reactants, and then you have their stoichiometric coefficients, and then you have the absolute standard entropy of each one of those. And then you just add them all up, just like you would with an enthalpy calculation. And so then what if you've got an entropy of reaction that's away from the standard temperature? What you'll need is your delta Cp, which, remember, is just a sum over all of your products and reactants, stoichiometric coefficient, and then the heat capacities of each of those. And then once you know that, your delta S standard for the reaction at some other temperature T is going to be equal to the delta S standard of reaction at the actual standard temperature plus an integration from the standard temperature, which is, remember, is 398.15 Kelvin, up to the temperature that you want, delta Cp divided by T prime dt prime. And I'm using primes to differentiate between the variable inside the integral and the boundary of the integral that you want. And that's it.